All right, analytics. Hopefully you're all here because you want to better understand the hype. And there's a lot of hype going on about analytics, right? And why wouldn't there be? Vendors want to sell their services, and if this is something that can help them sell their services, they're certainly going to hype it. And of course, we also want to understand predictive modeling basics. So let's get into it. First, a little legal disclaimer. You will learn a little bit about statistics tonight. This will not necessarily qualify you to be data scientists in and of itself. So if you're going to start doing multivariate statistics, in the same way that you might go to a dentist to get an oral procedure, perhaps you should go to a statistician to do some multivariate statistics. Yes? Hopefully you would agree. Also, statistical approaches sometimes require perseverance. If the first instance is a failure, well, you might have to wait it through, right? Because we're dealing with laws of averages. So, context. How many here have heard of the Fourth Industrial Revolution? You got 1, 2, 3, all right. So it's a way to conceptualize things. So the Industrial Revolution in general is just everything since we had machines. But you can further split it up. It started off when you had mechanization, water and steam power. And then eventually we ended up having electricity, which greatly accelerated things. Having motors really helped with horsepower. Just a second. Okay, we're back to normal. And upon that glitch, let's talk about computers. We had computerization come along, and that greatly accelerated things too. And automation. And now we're getting into the Industry 4.0, where we have devices talking to devices. Most people in this room probably have a cell phone in their pocket, which can perform 1 billion calculations a second. Yes? And these devices can talk to each other. And you can have robots, which are fixing robots. It's getting fairly dynamic. An interesting thing about these industrial revolutions is that the effective IQ, and I use this term loosely because there are many different types of intelligence, the effective IQ to participate in the benefits of each successive industrial revolution tends to get higher. So as things get more complicated, you need to get a little smarter if you want to participate in the benefits of the new advancements. And this is an additional challenge because population is growing, which means there are more people that you have to compete with. So this is kind of a scary dynamic. Actually, if you're a really smart person, it's great because there's a lot of opportunity for you. But it still means there's a lot of work that you have to do to keep up. So there's a context. Now, a little thought experiment. I have 2 pictures here. These pictures are related. I want you to first look at the picture on the left and quickly frame in your mind what you think it shows you. Got an idea? Now let's turn our attention to the picture on the right. There we go. All right, now it's apparent. The picture on the left is a still motion capture from a little video of fireworks. Now most people when they see this, they think that they're looking at a picture of the cosmos on the left. But you add one more dimension, and all of a sudden you see a lot more data. And so the point here is that without the added variables, we can be left in the dark. Also, do you see anything else in the picture when you look at the video? Trees? An awning? Yeah, there's an awning and there's trees. There was more data in there. And it was in there. You see this blank space? You see that blank space? The information was in there, but it was hard to see until we brought in that additional variable. Right? So the overarching lesson of all this is that analytics can be as transformative to data as motion pictures were to photography. This is a concept I originally got from a book called Big Data. It's a good read. It's funny though, it quotes Google flu, which later became a parable for overfitting data. So the book's a little outdated already, but still a good book to read. So how can we use analytics in oil and gas? Well, there's lots of ways. Geologists can use it to improve their pay maps and optimize lateral placement, find out what zones we have. How can we wine rack our wells, or do we only have one zone that we can put a well in? Reservoir engineers can use it to figure out better what acreage is optimal for acquisition or for predicting optimal well spacing. The drilling engineers can better figure out their drilling tolerances so they can drill as fast as possible without negatively impacting the production of their wells. And they can also use it to predict equipment failure so that they can plan their preventative maintenance so that they have less downtime. That's also true for the completion guys. And the completions can also predict their optimal frac designs. How much fluid, how much sand, prop spacing, frac stage spacing, you know what I mean. There's all sorts of different things that we need to optimize, and multivariate statistics is a way to do it. We need to see better. We need to see at different altitudes and scales in many dimensions, because we record many dimensions of data. Analytics can help us with that, with the nitty-gritty details in custom projects or in the big picture, such as you might get in big data analytics. Because multivariate analytics can be used almost at any scale you can think of. But we don't just need to see from a high altitude. We also need to bring out the talons and bring something home to eat every once in a while. We still need the talents of specific disciplines, such as geologists, geophysicists, engineers. Analytics doesn't displace the subject matter experts. It helps orient them to the most important problems faster. And speaking of seeing, statistical tools can help declutter and clarify our data landscapes. When you go to the hardware store, you don't need to know how to smelt iron, mill carbide bits, or fabricate plastic handles, but you do need to know how to use that rotary saw so that you don't cut off your fingers, right? Same thing with statistical tools. You don't necessarily know how to, you don't have to know how to drive all the statistical equations on your own. You don't need a PhD in statistics, but you do need to know the dangers of using multivariate techniques improperly, right? The limitations and the dangers of the tools. So here's a data science Venn diagram. There are three main spheres of expertise that play into data science. The first and foremost is multivariate statistics. And then we need to bring in our domain expertise from the engineers and geoscientists and whatnot. And then often we need to add in some automation because we're dealing with large amounts of data. That often helps, so we'll need some hacking skills too. And in the confluence of these is where we find our data science. But data science can sometimes be done without machine learning, right? We don't have to have machine learning to do it. I'll talk more about that later. So another aspect of this is that because you have these three spheres, and because there's so much to learn, you often have to resort to teamwork. I'm not going to say that there are no unicorns out there, but if you're trying to find the unicorn of a data scientist who's fully competent in all three spheres, that can program in Hadoop and Python, also knows their multivariate statistics, and who is a geomechanical specialist, well, you're going to have a hard time finding that person, right? So teamwork is often necessary. You often have to have more than one person collaborating. Now, traditionally, data scientists tended to be programmers who were also good at math, or mathematicians who are also good at programming, and then they would collaborate with domain experts. What you see happening more and more now is people who are domain experts getting very good at multivariate statistics and then collaborating with programmers as well. Because in general, there's a huge paucity of data scientists out there. It's hard to fill all the needs, so you have more domain experts getting into it. I kind of fall in that wheelhouse. You know, my expertise is geology, but I'm also branching into statistics. Another way to think of these is in terms of automation, validity, and intuition. This is a little framework which I came up with in my head. It just came to me a couple weeks ago. But I like it a lot because it makes sense, right? Machine learning lacks intuition. And if you're automating a bunch of processes, but you're not using statistics, it lacks validity, right? You're not doing your due diligence in your risk assessment. And when we talk about parametric models and non-parametric models, and I'll explain all that later on in the talk, we find that the non-parametric models, which tend to be artificial intelligence, machine learning, neural networks and whatnot, they tend to reside a little bit closer to this side, and then you have your parametric models, which tend to reside over here. The diagram isn't perfect. It's a two-dimensional diagram. It's a lot more dynamic. Of course, you can have plenty of automation factoring into parametric models, but you get the idea. So why multivariate analysis? So don't just take it from me. Here's a nice quote from some professors from my alma mater. The exclusive use of univariate procedures, and I'll add in bivariate as well, with multivariate data sets is no longer excusable. There's a better way to analyze our data. We should be using the best tools available to analyze our data. So let's just talk about data. Univariate, what do we do? Traditionally in univariate, we have box plots, we have histograms, we have summary statistics. Throw in the second dimension. Here I have a well log here, gamma ray, and deep resistivity. I've log normalized this. You can fit a trend line on it, start quoting R-squared statistics, although you should be very careful with R-squared statistics. If you want to get one of the professors at A&M very flustered, start quoting R-squared statistics. He doesn't like them very much at all. There's a lot of problems with that. I get into that in one of my other talks. Trivariate data, let's add in neutron porosity here. We can start seeing a lot more than we did in the simple bivariate plot, right? You can see a lot more detail about what's going on. But there's still a lot more we can see. Let's go ahead and overlay a photoelectric effect on this and look at how much more we can see. There's one of these blades of data which is now being nicely resolved, but there's still a couple other blades of data which are not yet being differentiated. So we still need more variables if we want to properly quantify all this information. But the problem is we've kind of reached the extent of our visualization capabilities, right? If I increase the size of these dots and give them different shapes, well, then they start obscuring the dots behind them. I've reached the limit of visualization. And that's a problem, because I still have lots of other variables I need to look at. So I'm going to need some multivariate techniques to do that. Now, if you decide to start your journey into big data and analytics, you're going to have to start small and early. You're going to have to start crawling. And after you start building competence, you might get to the point of walking. And eventually, you might get to the point of running. But you're going to have to do this individually for multivariate statistics and for big data. Right? These are two different competency sets. It's kind of like myself and my wife. She's very good at some things, and I'm very good at some other things. But we have to work as a team together. Right? So big data is not the same thing as analytics. Analytics also is referred to as data scientists. Data science, you'll hear me using that term as well. Okay? So this is the overall framework for the rest of the talk. I'm going to talk about the different portions of the analytics journey. Data collection, visualization, modeling, and predictive analytics. So starting off with data collection, we collect a lot of data and we have to prepare it for analysis. And it takes a long time to collect our data and to clean our data. It's kind of like the difference in time between making a bullet and shooting a bullet, right? Predictive analytics actually doesn't take that long compared to the gathering of data. So this is a big problem for companies. How do you shorten those lead times so you can get to the juicy predictive analytics that you're wanting? Well, one way to do it is to teach the why. Educate your workers as to the end use. Help them understand what analytics is all about and help them feel vested. When you consider that a lot of automation in factories, when they bring a robot in, that robot can displace 6 workers. When people hear about analytics coming into the corporation, they might start feeling a little threatened by it. They might even work counter to it. So you need to make them feel like they're part of it, make them feel vested and valuable. And then they're more likely to prepare the data in a way that will be more amenable to the analytics that you're going to want to do later. You need them. No, of course, setting best practices as well. Once you have a lot of data, if you want to do analysis on it, you're going to need to pull it in one place so that you can query the information that you want to analyze. This is often referred to as putting data into data lakes. And then querying the data, there's many different tools to do that, and then eventually getting onto the analytics part. There are many different platforms for doing this. You may have heard of Hadoop before, or Python. Hadoop is an environment, an ecosystem for other programs, but the core of it is distributed computing. If you have a 10 terabyte file and your wonderful desktop machine only has 64 gigs of RAM, it's going to take a while to push that big file through that RAM. But if you spread the workload across a whole bunch of server nodes, you can get your results back in a fraction of a second. That's what a lot of this is all about. Now, a lot of this software is totally free, 0 cost. But the problem is you're going to be programming in a Linux environment to use it, and that takes a long time to get to competency. So the big obstacle for most organizations is the time to competency, getting people who already know how to program or teaching your own people how to program in these environments if you want to do the data mining and querying of your data so that you have the data tables that you can eventually take on your predictive analytics. Now, data visualization, which we did a little bit of earlier, is very important because it ties into the intuition part. It helps our domain experts enhance their intuition of what's going on in the data. So you should always look at your data every single time. Don't just jump straight to the statistics, look at your data first. It does have some drawbacks though. it tends to have a rear view perspective. You're looking at what has happened, not what's going to happen. So you have to keep that in mind. Also, I already mentioned we're limited in the number of dimensions that we can show at one time, at least with traditional visualizations. Well, multivariate statistics to the rescue. We have a lot of tools for data exploration that we can resort to. Perhaps you've heard before of principal component analysis or cluster analysis, right? These are great tools for exploring our data. I'll just cover a couple of these, but one thing to keep in mind first, these methods aid in data exploration. They are not predictive analytics in and of themselves. You can use the results from them to help build predictive analytics, but these are data exploration tools. Now, Scatterplots is simply when you take every variable and you cross-plot it with every other variable. Here I've already color-coded some clusters in. I can start seeing patterns where I have linear relationships, for example. Then you can also put up some correlation matrices, or you can do color maps. I personally don't care for color maps because I can color code my numbers, and then I get the colors and the numbers. That's my preference. Then you have principal component analysis. Now, say you're plotting two variables against each other, and you draw an ellipsis that encompasses the variation in the data. You can characterize that ellipsis with two axes, the longer one being the first principal component, and the second one being your second principal component, right? So you can simplify the data. Now, a metaphor that most geologists will probably appreciate is consider if you have a fan of sediment on a perfectly flat surface. Presume it's more elongate than wide and that it's fairly symmetrical. In this case, the dip is your principal component, your first principal component, and your strike is your second principal component, right? And then your thickness is your third principal component. And perhaps your grain size distribution is your fourth principal component, and so forth, right? With each principal component being perpendicular to all the other principal components. So say you had 12 variables and you had 12 principal components. They would all be perpendicular to each other in 12-dimensional space, which is a bit of a brain twister, but that's how it works. So here's a little example from the log data I was showing earlier. And you can see atom size. So these make sense that those correlate, but this is a great way to explore your data. Speaking of which, I have a great example here. There's a student up at OU named Gabriel Machado. If anybody has an internship for a geophysicist, he'd love to hear from you. But he's done work with eigenvectors to identify fault swarms in different horizons in seismic, automatically. So instead of having to go through and pick every fault by hand, you just go through and you run some eigenvector analysis, and it highlights all your fault swarms. It's fantastic, because if you want to drill through a horizon that's more fractured because you might get better production from it, well, there you go. Isn't that spectacular? So, but again, this isn't a predictive modeling. This is exploring the data you already have. So this isn't going to tell me where the next fault is going to slip. This is showing the faults that already exist. Cluster analysis. There are many different types of cluster analysis. The most popular are hierarchical and k-means. There are others as well, like self-organizing maps, which are not the same kind of maps that we normally deal with. If one of these clusters happens to properly characterize my pay, I can then build a predictive model to target that cluster and other wells, right? So this is a data exploration tool, but again, I can take pieces of it and incorporate it into a predictive model later. So on that note, let's start moving toward data modeling. After we get past an obstacle, there's a chasm we need to cross. And that chasm is our fear. A lot of companies still haven't started doing analytics because they're uncertain about its utility. The irony being that we use analytics to reduce uncertainty. We use it to increase our rewards. We use it to decrease our risk. How much of your career is spent evaluating risk? Another aspect is that if you delay the implementation of analytics, it works against having an early mover advantage. This is a well-known part of the technology adoption life cycle. When there's a new technology, even if it's bona fides or well-established, a lot of people are hesitant to adopt it. I saw this with the iPhone. It came out in, what, about 2006 or so? It didn't really become prevalent amongst everybody until a couple years later. There was a stall in the adoption. So the objective of this talk and the other lectures I give is to help people become comfortable with analytics to the point where they're comfortable starting an analytics program in-house that they can then benefit from and stay competitive with the competition. Because I assure you, I have classmates who are also in oil and gas companies, and you will be competing with their predictive analytics skills going forward, right? So my talks help build a bridge. Hopefully you'll decide that you're comfortable crossing the chasm. So let's learn a little bit about data modeling and validation. First of all, data modeling, if you start doing some predictive analytics, you're going to have to pick a side. Do you want a parametric model or a non-parametric model? What do I mean by parametric? Well, I'm talking about a parameter, which is defined with a mathematical equation, like the slope of a line. Be it a linear slope, a logarithmic slope, polynomial, what you name it. If it can be described with a mathematical function, we refer to it as parametric. There's some great pros to parametric models. First of all, they're transparent. You can look inside your box and see what's happening. That's wonderful, especially if you consider yourself a scientist and you believe in the scientific method where other people can verify your results. And also, they give superior interpretive powers. They allow for high-level comparisons of different variables' effects. And they have less risk of having an invalid model without knowing it, because you can see inside the box and see what's going on. Parametric models are more useful when quality is paramount. Say, if you're going to buy 30,000 acres in the Permian and you're going to have to spend $1 billion, you might want someone else to double check your work. They can double check your work easily if you have a parametric model. Now, there's a lot of hype about the black boxes, the non-parametric models. These typically are where the artificial intelligence, machine learning, neural networks, and deep learning fall into. Now, they do have some pros. They have their uses. They're able to handle gargantuan and continuous streams of data. And they can be deployed more quickly in many instances. And they're more useful when processing speed is paramount. So for example, if you have sensors in a drilling bit, you're drilling several thousand feet below the surface, you're sensing the conditions of the rock around you, the bulk density, the brittleness, the porosity and whatnot, and you need to adapt on the fly. Well, you may not have time to send that data to surface, build a parametric model, send instructions back down. It'll be 50 feet beyond where you were. It needs to make a decision right now. That's where having some artificial intelligence embedded in the tool might be a better choice for you when processing speed is paramount. This is often the case with driverless cars as well. I like to think of these two different boxes as being the brains and the brawn, right? Computers are very strong, and our brains are very smart. So fleshing this out again, because repetition is the mother of learning, it's a little bit harder to set up your parametric models. It takes a little longer to get your initial results. But it is easier to track your data lineage, and by that I mean what's happening to your data within the model. It's easier to find and mend your model weaknesses. And it's easier to verify your results with third parties. It's easier to get a peer review of your work. And then once you have, you can track your variables and their individual effects and compare them, what each variable is doing versus the others. And it's easier to prevent the violations of your critical assumptions and maintain valid models. And then the black box is the opposite. You run the risk to a greater extent with a black box model of wasting company resources on invalid models without even knowing it. This isn't the same kind of quick response that you get in a wood shop where you cut off your fingers and you know it right away. You can make some horrible mistakes with non-parametric models and not know it until way after you've already deployed a lot of capital. So if you have somebody come to you with a black box solution promising you the moon, proceed with caution. I'm not saying it's not the right solution, but you should make sure that everything is measured and double-checked and triple-checked. Now, there's also another option, the gray box. It is possible to have some elements mixed between the parametric and the non-parametric models. And in certain scenarios, that might be the best option for you. Now, here's a little example of a gray box model. Here's some data. This is actually a sine curve that had a random function applied to it to generate a random curve. But it's not very amenable to a linear trend line. It's not even very amenable to a quadratic trend line. But hey, if I segment this data into a whole bunch of segments, I can apply linear trend lines to each individual segment and then describe that with a piecewise function. Right? So I still have the linear trend lines, which is more the parametric approach, and then I have these piecewise functions, which is an aspect of the non-parametric approach. Now, if I'm only doing this for 1 out of 20 variables, it's more of a gray box. If I'm doing this for 2 or 3 variables and I have these piecewise functions going in multiple dimensions, it's already getting so convoluted, it's a black box. Right? It's really getting hard to track what's going on in any point in space. For those interested in learning about machine learning, I suggest you start off with the Markov decision process and Monte Carlo methods. I'm not cruel enough to read this whole slide to you, and I don't have enough time. But machine learning types. Artificial intelligence is an overarching term that captures all the different machine learning. Machine learning is a subset of artificial intelligence. It can improve with experience. The more data you feed in, the better it can get. Quick caution, all of the machine learning types, they might have pattern recognition. That does not mean that they have reasoning and cognition. Keep that in mind. They're not able to think, they're just able to recognize patterns. It's not the same thing. Artificial neural networks, they have interconnected data nodes. The results can be hit or miss. If you're not going to train your neural networks, a very cheap alternative to them is a copper penny. You'll get the same outcomes from flipping it. How do they work with artificial neural networks? You have a bunch of input nodes, and then it has a number of hidden layers, and then it has an output layer. And basically what it's doing is it's trying every transformation and calculation it can try, and then it assigns what's called a credit assignment path that's deemed as being the best path, the best outcome. And then when you get into deep learning, that's when you have multi-layered neural networks with iterative caps, usually greater than 3. And you can get some pretty good results out of deep learning sometimes. They're able to train themselves a little bit better. And by the way, they've been around since the 1970s. It might be new to you, but it's not new. Right? These have been around a long time. There are many different types of neural networks. Right? So when we talk about reiterative caps, they can be run through a bunch of different types of neural networks. I find it interesting that the most complicated neural networks have about the same neural complexity as an earthworm. The difference is that if you take your dinner fork and drop it to the floor, the phone in your pocket can do 1 billion calculations before that fork hits the floor. So these might be simple, but you can run a lot of data through them. So you can still get some pretty impressive results out sometimes. There are pitfalls to machine learning. I won't go through all of these again because I don't like torturing crowds. I do like having captive audiences, but I don't like torturing them. The one I'll mention first and foremost here is this second bullet point. Machine learning frequently will use the y variables that you're trying to predict as the x variables that you're using to predict. And then they'll go through very elaborate processes to prove to you beyond a shadow of a doubt that 1 is equal to 1. This is a very common problem with them. They don't know what's what. They don't have the intuition, remember? They don't have the intuition that you and I have. So remember, machines are useful, but they have to be used properly. You have to set them up right and point them in the right direction. Now, validation. There's no point in modeling unless you validate, because almost everything has bias. If you're a manager and you have a bunch of employees, are you going to let them do their own employee evaluations at the end of the year? Will they be able to give unbiased assessments of themselves? Probably not. There's a lot of bias, so you have to train your data. And how do we do that? Well, we take our data set and we split it. And then we use part of it to train the model. And then once the model's trained, we run that model on the validation set and we see what comes out, whether it's statistically significant or not. Now, if you're using a parametric model, you may only have to do 1 split, right? Training and validation. If you're using a non-parametric model, people frequently do a 3-way split because they trust the non-parametric a little less, so they train it, and then they validate it, and then they validate it again because they don't trust the machine learning quite as much. So there's a lot of different things to do, that you can do. Now, in general, the objective in training is to prevent overfitting. Overfitting is when you have high precision but low accuracy, right? So again, remember, your probability values, if you don't have a validation set, are worthless. And this is why, because they might have a nice cluster of outcomes, but they won't be where you want them to be, right? On the other hand, you can have underfitting. That's often when you can't see all your data, like when you're with the visualizations, we couldn't plot all the variables at once. So the visualizations were inherently underfitting the data, right? If you have 20 variables that you need to look at, but you can only look at 4 or 5 at a time, it inherently underfits the data. What we want is a robust model that hits the target or gets close to it every single time, right? So a quick question to ask yourself: how much of your career will have been spent assessing risk? And are you doing it right? So let's learn some statistics. First of all, in statistics, we take samples. And those samples are comprised of individuals. Individuals can be people, places, or things. Sometimes we refer to them as objects. And on these individuals, we will measure multiple variables. Now, these variables can be categorical, also known as nominal, or they can be ordinal. Ordinal variables have an implicit ordering, like small, medium, large, poor, medium, fair, implicit ordering in the ordinals. And then you have, and both of these together are qualitative. And then you have numerical variables. You can also call them continuous variables, and those, of course, are quantitative variables. So a quick little thought experiment. If I have a column of data, which is primarily numerical, but somebody has put a bunch of text comments in it, if I throw that into a machine, what data type is it going to presume? Well, unless I'm talking about dirty data, the issue of dirty data. It goes back to the data preparation problem that I mentioned earlier, right? If you have text mixed in with your numbers, the machine learning might presume that it's handling categorical data, and it will treat it as such when it starts running the model. And the outcomes that you will get out of that model will be drastically different than what you were actually hoping to get. That's just a little food for thought. If you have a data scientist building a parametric model, which is transparent, you can see what's going on, it's a lot easier to correct errors in your model. So frequently what's happening is we're wanting to predict a variable, let's call it y, and we're going to use a whole bunch of x variables to do so. Now the x variables can be called predictor variables or explanatory variables, and the y variable can be called the response variable or the dependent variable. And the number of x variables that we use will be denoted with the letter k. And we have a lot of them. I hope you believe me by now. We have a lot of variables in our industry. It doesn't matter what discipline you're in, you have a lot of variables to take into consideration, right? And again, analytics can give us that high altitude view so that we can know what to focus on. Do we have a lurking variable that needs to be added into the model? Or do we need to focus our attention on one specific variable where most of the bang for the buck will come? Well, again, analytics helps orient us to what matters most. So a little more statistical lingo here. When I have a population, we'll use the letter mu, the Greek letter mu for the arithmetic average, aka mean, and we'll use the Greek letter sigma for the population standard deviation. Now, if I go to the beach with my kids, and I hope someday they will be aspiring geologists and ask me, Daddy, what's the average size of a grain of sand on this beach? Unfortunately, Daddy is not rich enough, and Daddy will not have enough longevity to properly measure the size of every grain of sand on that beach. So what will Daddy do? Daddy will take samples, and he will refer to the mean of the samples as x bar, and he'll refer to the standard deviation with an S or with a sigma hat. Didn't write that up there, I didn't want to confuse you. Now, geologists, do you like quick look techniques? This is a fun one. So if you're wondering where the first standard deviation is on a normal distribution, if you look at where the curve goes from being concave to convex, that inflection point will typically be your first standard deviation. Right? That's a nice little trick. And when the population is skewed to the left or the right, we're referring to the tails, right? We're not referring to the lump under the hump. We're referring to the tails of the scale. Why? Because we're skewing the means. That tail is going to pull your mean away from your median, right? That's why we're referring to the skew as being in the tails. It pulls the mean. And that's a problem because there's a lot of statistical tools that we cannot use on on populations which are not normally distributed. Oh no, we don't know everything. But guess what? We got a lot of tricks up our sleeve. If I take a whole bunch of samples from that population, and then I take the means of those samples and plot the means, a whole bunch of them, those means will be normally distributed. This is referred to as the central limit theorem. And I can do a lot of the cool statistical tricks on those means. There are other things we can do as well. So we do not know everything, but that does not mean that we know nothing. Now, regression. What is regression? It sounds like a fancy term. It's actually pretty straightforward. We're taking the arithmetic average of y for a given value of x. That's all it is. It's pretty straightforward. And presuming that our y's are normally distributed and our x's are normally distributed, we're off to the races. Another way we can annotate this is y bar for each value of x. And another way we can annotate it is as y hat. I've put up a picture of a lovely lady wearing a hat so that you can remember, whenever you see a hat on a variable, it's a modeled number. Yes? Now, the mean of y is how we estimate y, which is how we predict y with a model for y. So these are synonyms, right? Mean of y, estimated y, predicted y, modeled y. They're all referring to the same thing. They're referring to y hat. And with just one x variable, it's pretty straightforward. You have your y-intercept, and then you have your trend line, right? And that trend line has a slope. This should look familiar to you. It should remind you of your junior high algebra days, right? But why in the world, why, oh Lord, are we putting the y-intercept at the beginning of the equation? Well, because we have a lot of x's. And when we count, we like starting at 0. So we have b0, b1, b2, and so forth. Yes? Now let's consider a three-dimensional example. We're going to predict y from two x's. Where both x's are equal to 0, we have our y-intercept. We can see that 1 has a negative slope, y2 has a positive slope. Now, for each x, when the other x is not equal to 0, the effective y-intercept will change. However, the slopes will remain constant. Isn't that nice? It allows us to compare our estimated slopes across all values of all x's. This gives us tremendous predictive powers. Now, this is just a three-dimensional example. In real life, we have far more than 3 dimensions we're working with, typically. How do we visualize it? Well, if you're dealing with a parametric model where you can quantify the slopes, it's easy. You just throw up a tornado chart of the slopes. Here I have 18 variables. I am now looking in 18-dimensional space, and I can see almost exactly what's happening with my model. It's a thing of beauty. But we have different types of models. So getting back to the parametric versus non-parametric, what we find is that these slope estimates we get are valid for the entire range of modeled possibilities, whereas with a combo model, the slope estimates are only valid for partial ranges of the model possibilities. And then with our non-parametric models, we have derivative estimates, which are derived locally from highly convoluted multidimensional surfaces. So last week, I got to talk to 2 data scientists working for a company whose market cap is in the hundreds of billions of dollars. Their data science team has over 200 data scientists, half of which have PhDs, typically in mathematics or statistics. Which type of model do you think they prefer? They prefer the parametric model, because they don't just work in a cave, they have to report their results to management. And it is far easier for them to convey what they've found using parametric models than with non-parametric, because the validity of their interpretations have a much broader applicability to market conditions using a parametric model. Thus, they have far more utility to management. I can't disclose the name of the company, but there you go. And even when we're doing a parametric solution, it can still get complicated. We're not just dealing with linear trend lines. We can use all sorts of stuff. So we can still characterize highly convoluted multidimensional surfaces with parametric models and still get our slope estimates and still have our widely applicable results to report to management. Here's a nice little thing. Smart brains utilize Braun. You've probably gathered already that I have a strong preference for parametric models, partially because I've been taught to by some very smart people. But we don't just use them. We also exploit the non-parametric models to find all the nuances out there about what's happening in the multidimensional space. And we can compare them, and then when we have discrepancies, we know that we might have a lurking variable that we need to go hunt for to add to our model so that we can better characterize our data. Right? So we can use both and still end up with a parametric model that gives us a full utility of interpretability. Now I'm going to give an example. I'm sorry I can't give an oil-filled example here. I am working on one, but I'm not at liberty to disclose it. So instead I'm going to use a sports analogy. I presume at least most of the guys will enjoy the sports analogy. I don't know if you ladies are sports fans too. But here I'm going to model NBA salaries based on player performance. Now, you might notice I am modeling numeric variables and categorical variables in this model. Furthermore, I get to solve for these all simultaneously. I am not isolating variables and testing each one individually. Can you imagine how that would go down in an NBA playoff game if you told all the fans who paid who knows what for their seats, sorry, we're only going to do free throws tonight because we're trying to isolate a variable. The fans wouldn't stand for it. So we don't have the luxury of collecting just one variable at a time and holding everything else constant in the real world, right? But we don't have to, because with multivariate statistics, we can still determine all of them simultaneously. It's a thing of beauty, and I would have saved so much time on my first master's thesis if I'd known this. If only I'd known back then. So the first column here is our, but if I'm not an avid sports fan and I don't know which one of these variables is actionable or more important to retain, I might have to go talk to a subject matter expert to get their input as I continue building this model and culling out variables that are less important. Right, I'm going to go ahead and skip that part. So getting back to a little bit more statistical lingo, because I can tell that you all love it so much. Residuals. How many people here have heard of residuals before? All right, a decent portion, maybe about 20%. I went to every multivariate theme talk that was available at AAPG. I didn't see anybody put up a residual plot. And yet they're what we use to establish validity in a statistical model, more often than not. Now, residuals are when you subtract the point from the line from the actual point. So you can also call them errors. They're the error that the model makes in trying to predict the value. So if you want the model to predict this value, but it's off by that much, there's your error. But it's a little more clear to call them residuals. If you sum them up and then minimize the summation, which is called the residual sum of squares or sum of squared errors, then your minimized residual sum of squares gives you your best linear trend line fit in the least squares sense. Anybody here who has ever fit a trend line has had this happening in the background, whether or not you realized it. So that's one of the great utilities of it. And then again, they're great for assessing randomness, because what you're doing is you're subtracting out the slope, and then it's easier to see patterns in the data. There are critical assumptions that must be met to have a valid statistical model, and most of them are assessed by looking at your residual plots. Your residuals need to have a zero mean. Residuals need to have constant variance. This is the most important of them all. Randomness. They have to have randomness, or else it will invalidate all your inferential tools. They need to be independent of each other, right? This is often a problem with time series data. Think about the production of a well, where the production at every day can only move so far from the previous day, right? You have to account for those effects that we often call serial correlation or autocorrelation. You have to account for those to compensate for this lack of independence. And also you need your probability distribution to be normal. So, and you've all heard the term lies, damn lies in statistics. I don't remember the name of it's a prime minister in England in like the 1880s that said that. That's referring to when you violate your critical assumptions, right? Then your statistics are worse than damn lies. You have to validate your models. Look at your residual plots. Now here's a few examples. This is from and then again, my smart brains are going to utilize the Braun, and I'm going to compare what I'm getting with what a non-parametric model would give me. And for the most part, I am quantifying some pretty convoluted structures in multidimensional space pretty well. With a few exceptions, I can see some divergences in here. That means I need to probably quantify some additional indicator variables. Expand my model a little bit more, bring in another variable, make sure that I have everything parameterized properly. And then once I stabilize my model, I can start doing predictive analytics. Let's just presume I have a stable model here. And you can see I still have a couple categorical variables. I have a bunch of numerical variables. And I can start making inferences. Is I can start saying that for each 1 unit change in X, I will have a such and such unit change in Y. And this is what I end up going to management and predicting. For every $1 increase that you spend on frac sand, you'll get this much increase in production. Think some managers would like to hear information like that? To know how much of an impact each variable is having on the ultimate producibility of a well? And there's a little dirty secret I've been keeping from you. I actually modeled the log of NBA salaries. So the math gets more complicated, right? But if I do some additional math, I can make conclusions like a 1 unit change in X will give me a % change in Y. Managers often like this better. They like thinking in terms of percentages more than in terms of unit changes. So it's not entirely a bad thing. So to kind of sum this up, we have to hunt for lurking variables, and we have a bunch of tools to do that, right? You should not run with a model until you have stabilized it, right? Don't just take your initial results when things aren't valid and report them. That's what we call a DCM model. Don't come back Monday, right? And you might need some input from your subject matter experts to build the model correctly. And if you're doing a parametric model, you'll have the wonderful benefit of being able to track parameter estimates for each variable across all values of each variable, which I propose to you is tremendously useful. And that gives us a high altitude view that we need to focus on the business problems that we're faced with. And we have plenty. So just to conclude, everybody loves quoting Einstein, right? Make everything as simple as possible, but no simpler. If you cannot properly quantify your data with a bivariate plot, don't do it, right? If you need at least 7 variables to quantify your data, you better use the 7 variables, right? Another way to refer to this is with a well-known acronym, the slight twist. Keep it sophisticatedly simple, please. So this is actually the first part of a 5-part series of talks. I hope you've enjoyed it, but that's all I can show you tonight. And
Are there any questions?
So the financial takeaway I got was dollar. The effect on oil and gas and plumbing analytics. What do you see right now from your perspective as the limiting factor of this being implemented? Is it people not lacking the technical know-how? Is it bad data? We don't have that.
I think that the main challenge right now is competency. Not many people know how to do multivariate statistics competently. I saw a lot of people trying to do it at AAPG. I saw people putting up graphs, and I'd look at the graph and I'd know right away that they had a problem with non-constant error variance, which was invalidating their model. I didn't have the heart to get up and tell them that, though, not in front of other people, that would be rude. But a lot of people are starting to play with it. But again, kind of like with tools, my son would love to go into my tool shop and start playing with tools. I won't let him because he's not competent yet. I can't trust him to not cut his arm open, right? It's different with statistics because you don't see the blood right away. But I think it's going to be a while before we have enough people in industry which know what they're doing to do it right. And I'm afraid that some of the people who aren't doing it right will put a bad flavor in the mouths of others.
Okay, Andrew, on behalf of HGS, this is a speaker award.
Awesome. Rattlesnake limestone.
Rattlesnake limestone.
Yeah.
If there are any more questions you'd like.